Yeah, good morning all. So today I'll be dealing with the last part of the fourth module which ma'am has skipped, that is Widlar current source. I think all other portions ma'am has covered, only this portion Widlar current source is pending, so that I'll be taking now. Okay. So this is going to be a very important part of this particular module, Widlar current source. So I would like to explain just about other current sources in a brief manner so that we can specify the advantages and requirements of Widlar current source. So as you can see in the second part of this particular module, you will be dealing with different types of mirrors. Okay, like cascode Morse mirror, followed by bipolar mirror with base current compensation. Then it is followed by Wilson current mirror, then Wilson Morse mirror, and finally the Widlar current source. So all these mirror circuits as well as the source current sources, it has got its own benefits and features. Okay. So from the name itself, the first part, that is a first current mirror circuit, that is cascode Morse mirror. This particular mirror circuit is suitable for cascode amplifier. You know what is mirror? Mirror is nothing but a circuit, an active loaded circuit which is used to steer a required amount of current from one location of an IC to another point of an IC. Okay. You know that in an integrated circuit, you are going to have different microelectronic circuits fabricated under a one silicon wafer. So each of these discrete components, they will be using different currents. Okay, maybe one part of the IC will be using 10 milliamps, the other part of the IC will be using 5 milliamps. So you can't produce 10 milliamps, 5 milliamps, 2 milliamps, it's all these current sources in one IC. So again, that will become quite complicated, and it will lead to a situation where you won't be able to fabricate this current sources, all these current sources in one IC. So what you will do is you will be using one current source, and from that current source you will be steering required amount of current to all other parts. Okay. So that is what is known as mirror. Okay. So that is the significance of mirror. So in the fourth module we have been dealing with this cascode amplifier. So the cascode amplifier always require a current source which is able to produce an output resistance that is convenient to that particular amplifier. Okay. So a cascode amplifier, it normally requires an output resistance of A0 into R0. A0 is the gain of the transistor and R0 is the conventional output resistance of a common source. Okay. In a cascode, you have both common source as well as common gate. The common source is the first stage. The common gate is the second stage. Common source is having an output resistance of smaller than R0. Okay, which is amplified by A0. So the total product is A0 into R0, which is the actual output resistance of the entire cascode amplifier. So that output resistance we have to set for the current source also. Then only the resistance matching will occur and maximum current can be delivered from the current source to the load. Okay. So my intention is to have a comparison of all these four circuits with the Widlar current source, what we are going to deal today. All these four current mirror circuits have been taught by Neetu ma'am. So I just want to compare all the four things with respect to the Widlar current source, what you are going to deal with today. So in the cascode Morse mirror, we are able to generate an output resistance of R0, R out is equal to A0 into R0. Okay, we can look into that. See, See, this is a cascode Morse mirror. Already it has been taken, and here the output resistance of this particular circuit is GM3 into R03 into R02. What is GM3 into R03? GM3 into R03 is the gain of the third transistor. See, this is your mirror. This is your mirror circuit. So Q3 is the common gate and Q2 is the common source. So the gain of Q3 is GM3 into R03 multiplied by R02. R02 is the output resistance of Q2. So that much output resistance this entire circuit is giving. Okay. That was the conclusion for cascode Morse mirror. Then followed by that we have discussed about the bipolar mirror. Bipolar mirror means by using BJTs. Okay, by using simple bipolar transistor BJTs, it was able to derive an equation of current transfer ratio I naught by IRF. So this was the equation for current transfer ratio. I naught by IRF is equal to 1 divided by 1 plus 2 by beta square. You know what is beta? Beta is a current gain of a transistor which is very large, about 100, 101 it will be. So 2 by 100 square is still small, isn't it? 2 divided by 100 square is very much small, which can be neglected with respect to 1. So always I naught by I ref is equal to 1 is to 1. So this is having a very large depend on 2 by beta square. 2 by beta square is very small, so as a result the ratio I naught by I ref will become 1 is to 1, which is acting as a perfect mirror. Okay, for every perfect mirror the ratio of I naught by I ref is equal to 1 is to 1, means whatever be the reference current, that will be the output current. Okay, there is no change between the reference current and output current. So the conclusion is this particular circuit of current mirror using, that is bipolar, using base current compensation technique. This is bipolar mirror with base current compensation technique. This particular mirror circuit was used to produce a current transfer ratio of 1 is to 1, which is quite appreciable for all the current mirrors. So that was the conclusion of the second mirror. Then third mirror, Wilson current mirror. Wilson, named scientist and researcher, he has designed a mirror circuit. Again, this is a typical BJT only, it is not MOSFET. So whenever you are asked to design a Wilson current mirror and asked to derive the expression for current transfer ratio, don't go for MOSFET. That is Wilson's MOS mirror. Okay, it will be specified like Wilson MOS mirror, then only you draw the MOSFET terms or MOSFET device. Here it has been constructed by using symbol BJT and it is called as Wilson current mirror, which is a typically used with bipolar configuration. Okay, again this was derived by Neetu ma'am, and here the derivation goes like this, and the ratio is same, I naught by IRF, whatever we had derived in the earlier configuration, I0 by IRF, that is 1 divided by 1 plus 2 by beta square. So Wilson bipolar current mirror is having the same current transfer ratio as we have derived in the earlier part, that is a bipolar base current compensation technique. So only thing is that he has just redefined the circuit configuration. Okay, then later he has derived the output resistance also. Okay, the output resistance he derived for the circuit by using some KVL and KCL circuits. He was able to derive the equation for output resistance Vx by Ix, which was equal to beta R0 by 2. So this is the main drawback of this Wilson bipolar mirror, which is seldom used. Okay, so the Wilson's bipolar mirror was able to produce an output resistance of beta R0 by 2, which was not equal to a cascode amplifier output. Okay, so this particular current mirror circuit will not be able to suit the cascode amplifier. We know that the cascode amplifier is having an output resistance of A0 into R0 or GM3 R03 R02. Isn't it? GM3 R03 is nothing but the gain of Q3, and R02 is the resistance of second transistor. So altogether the output resistance will become A0 into R0, gain multiplied by the output resistance. That is the overall output resistance of a cascode amplifier, which is not at all able to satisfy with this particular Wilson's current mirror circuit, that is bipolar mirror circuit. So Wilson bipolar mirror is only able to produce a output resistance of beta R0 by 2. That is the main drawback. And later what he did is he replaced this BJT by using MOSFET. Okay, without any changes in the circuit diagram or configuration, he simply replaced the BJT over, that is by MOSFET, and he again derived the equation for Vx by Ix, that is output resistance, and he then able to produce an ratio Vx by Ix is equal to Gm3 R02 into R03, which was equal to A03 into R02. That will be quite similar as that of the output resistance of a cascode amplifier, so that he concluded that his Wilson's MOS mirror is exactly suitable for the cascode amplifier. Understood? So I repeat all the four current mirror circuit what you have learned in this module. First one was the cascode MOS mirror. Second one was the BJT with bipolar mirror with base current compensation. Third mirror, Wilson's bipolar mirror. Fourth one, Wilson's MOS mirror. Okay. The main differences between these four circuits is that even though they are acting as perfect MOS mirrors, but certain circuits are not providing the suitable output resistance whatever we want, that is a cascode amplifier want. Okay, the cascode amplifier requires an output resistance of A0 into R0. So your mirror circuit is also that is, it should also require the same output resistance, and only the matching will occur and maximum delivery of current will occur. Okay, so that can be satisfied only with the case of Wilson's MOS mirror, not Wilson's current mirror. Wilson's current mirror is with bipolar, though it is satisfying the I naught by IRF ratio 1 is to 1, it is able to produce the same current transfer ratio what we require. That is exactly a current mirror. But the thing is that it is not able to produce the output resistance what we want. Okay, if there is no matching between the output resistance of an amplifier and a current source, what is happening? Impedance matching will not occur and there will be some losses. So the required amount of biasing will not happen. Q point will not be fixed. So that will affect our gain of the amplifier. Okay, so we have to bias the amplifier properly. For that the exact current should be there. For that what should be there? The output resistance should be matched. The output resistance of the amplifier should match with the output resistance of the current mirror whatever you have designed. So that can be satisfied only with the help of a Wilson's MOS mirror. Okay, the difference between Wilson current mirror and Wilson MOS mirror is current mirror he has used only BJT. In MOS mirror he has replaced his BJT by MOSFET without any change in the circuit configuration or circuit connection. Only the device has been replaced, and what his conclusion is, he could able to satisfy the current transfer ratio 1 is to 1, that is it is acting as a perfect mirror, and apart from that he is able to achieve the output resistance which is equal to A0 into R0, which is always desirable for a cascode amplifier. Okay, so that was the four different configurations of mirrors. Now we will look into the last part of the fourth module, which was pending, that is Widler current source. See the difference here, it is current source. The earlier four versions was current mirror, now we are dealing with current source. Means the earlier four circuit was able to produce an output ratio, current transfer ratio 1 is to 1. Means whatever be the IRF that will be equal to I0. Understood? So I naught by IRF is equal to 1 is to 1. Earlier we have derived an equation, isn't it? 1 divided by 1 plus 2 by beta square. The value of 2 by beta square is very small because beta is large. So 2 by beta square can be neglected. So the current transfer ratio will be 1 is to 1. So all the previous versions of current mirror circuits was able to produce a current transfer ratio 1 is to 1. So it is known as current mirrors. But this circuit, Widler's configuration, this is current source, means we can design any desirable current. Okay, we will be able to produce any desirable current with respect to a reference current. Not that it is a simple mirror. Simple mirror means I naught will be equal to IRF. But according to Widler current source, this particular circuit configuration is able to produce any desirable current whatever the user want. Okay, that is if a particular IC requires 10 milliamps, the other part of the IC requires 5 milliamps, but unfortunately I have 20 milliamps of current source. So what I will do, I will be producing 10 milliamps as well as 5 milliamps from the input 20 milliamps by using some current source circuits or current steering circuits. For that I don't want a perfect mirror, because perfect mirror will get only will provide only 20 milliamps. Whatever be the reference current, that will be the output current. So if at all I require an output current which is not same or which is different from that of the reference current, then no longer I am not using mirror circuit. Okay, so instead of mirror circuit I will be using current source circuit. Got the difference between current source and current mirror? Okay, current mirror will always steer the output current which is same as that of the input current or the reference current, but current source will be able to produce any desirable amount of current from the based upon the reference current. That is a difference. So as you see the circuit, it is quite simple when compared to the previous versions of Wilson's MOS mirror or Wilson's BJT bipolar mirror, because there they are having three transistors, but here it is going to explore with only two transistors, so it is quite simple. The hardware complexity is quite simple, but you are going to use a particular resistance RE. Okay, RE is going to be an extra part here other than one transistor. Okay, and here you are having a reference current also. So based upon this reference current and based upon this resistance Re, we are producing I0. Okay, so the required amount of output current can be produced based upon the reference current and based upon the emitter resistance Re. Note that the two emitter terminals have been short circuited and the two base terminals have also been short circuited. So this configuration is known as Widler current source. So when you see this circuit, you can write two equations for the base to emitter voltages of Q1 and Q2. This is nothing but the transistor equation. VB1 is equal to VT into natural. You have familiarized with this equation in electronic devices and circuits, isn't it? This is conventional diode equation. That is, the base to emitter voltage is equal to Vt into natural log of IRF by Is. Usually it is I naught by Is, but as far as the Q1 transistor is concerned, here I naught is IRF. I naught is a collector current, isn't it? Collector current is something but reference current. So IRF by Is, where Vt is known as thermal voltage, which will be always a constant, approximately 25 millivolt. Because you know that this is a diode only. Base to emitter junction, it is a diode, isn't it? Whenever you take a transistor, it is having two junction diodes. So one of the junction can be assumed as a diode, and the diode equation I have written in equation number 1. That is VB1, voltage across the base to emitter junction, is equal to thermal voltage into natural log of I naught by Is. Is is the saturation current of a transistor, which will be always available in the data sheet. Okay, I reference is the reference current. Now coming to the second transistor, you are writing the same equation. The only difference is instead of I naught you will be putting, sorry, instead of IRF you will be putting I naught, because output current is I naught here, not IRF. Okay, so instead of IRF you will be putting I0. So VBE2 is equal to Vt into natural log of I naught divided by Is. Now divide these two equations. What you will get? Divide the two equations. So VB1, sorry, not divide, subtract the two equations. So VB1 minus VB2 is equal to, you can take V2 out, Vt outside, which is a common. Take Vt outside. So natural log of IRF by Is minus natural log of I naught divided by Is. Okay. So when you subtract, it will be going like this. You know that log A minus log B is log of A by B. Okay. So Vt into log of IRF by Is divided by I naught by Is. So Is will get cancelled. So VB1 minus VB2 equal to Vt natural log of IRF by I naught. Let it be in equation number 3. Now what you will do is take KVL, apply KVL in this particular loop. Okay. So as far as this particular loop is concerned, this voltage VB1 is equal to sum of the voltage across VB2 and the drop across RE. And the drop across RE is nothing but I naught into RE, because I naught is the current through the transistor. This current is flowing through RE as well. So the drop across RE is I naught into RE. Understood? So VB1 is equal to VB2 plus I naught into RE. Take VB2 left side. So VB1 minus VB2 equal to I naught into RE. So when you observe this equation number 3 and 5, the left side is same. So you can equate right side. So the equation will go like this: I naught into RE. That is, right side of equation number 5 is equal to right side of equation number 3. So as far as this equation is concerned, now you have got an expression for I0 in terms of RE and IRF. So if you know reference current and the resistance RE, you can design this particular circuit for any required amount of I0. Okay. Suppose you have IRF, it is given to you. I0 you wanted. Actually, you are designing a circuit for I0. So for the required amount of I0, you can design the proper value of RE, because RE is going to determine the value of I0 for a given value of IRF. Note that Vt is always 25 millivolt. Understood? So by changing the value of RE, you will be able to produce different currents. So this is what is the advantage of Wilson's current source, where he is able to steer any desired amount of current out of a reference current by using a small resistance value RE, that too with a simple hardware circuit only with two transistors BJTs. Okay, and please note down this particular equation for output resistance, and no need to design this or derive this particular value, because it is already known. For a common emitter transistor, the output resistance is 1 plus GM into RE parallel R pi whole into R0. You can note down this, no need for derivation. This can be applied to the numerical problems. You know everything. GM is a transconductance, R is external emitter resistance, what we have fixed in the emitter terminal, which is going to affect our I0. R0 is the total output, that is a second transistor's output resistance, this one. Okay, because you are taking the output from the Q2, so you will have an internal output resistance of this transistor Q2. So that is what is known as R0. R pi is the base internal resistance, or the input internal resistance, that is R pi. So here, if you note this equation, it is evident that the output resistance is increased above R0. Normally, the output resistance was R0, but by configuring this circuit, you will be able to increase the output resistance by a factor of 1 plus GM into RE parallel R pi, isn't it? Which is very much highly significant. So you are able to produce a very much high output resistance that is approximately equal to the output resistance of a cascode. You know that for a cascode amplifier, you are having a very large output resistance. Okay, so you should be always able to design a current source whose output resistance should exactly match with the output resistance of a cascode. If you are producing a current source having a very small output resistance, and if you are using that same current source to an amplifier, that will not match, because the output resistance of a cascode amplifier is typically very large. Okay, so care should be taken to design a current source or current mirror whose output resistance should be exactly large and same as that of the output resistance of a cascode amplifier. Then only proper biasing will occur. There should be impedance matching or resistance matching between the output resistance of a current mirror circuit and the output resistance of a cascode amplifier. Got the point? Okay. So once again, I'll repeat. This is a Bidler current source where he has used only two transistors and one resistance. So by appropriately designing the value of the resistance RE, he will be able to design any value of output current from the reference current. Okay. So for this, what he has done is he has written the equation for VB1 and VB2 in terms of IRF and I0. Then divide these two equations, sorry, subtract these two equations. So the equation will go like this. Then applying KVL to that loop, again you will get another equation, that is equation number 5. Then simply equating, you will get an equation that determines the value of I0 in terms of RE. So if you observe this equation, if you know the value of IRF and if you know the value of I0, because I0 is actually, it is to be designed. Okay, for a suitable value of I0 only you are fitting RE. Understood? So RE is to be designed for a required value of I0 and for a given value of IRF. So IRF will be given, I0 is a desired value. So according to that, you can fix the value of RE provided VT is known, because it is a thermal voltage of 25 millivolt, and the advantage is that it is providing high output resistance that is exactly matching with the cascode amplifier, and with a small constant current using relatively small resistance. Again, the circuit complexity is very less. So it is able to produce any desirable value of output current with a convenient resistance value, and again having considerably saving very less chip area, means hardware complexity is less. So it can be fabricated within a small space. Then again it is offering a high output resistance which is quite desirable for a cascode amplifier. Understood? So that is the end of this module. Now we'll go to some problems. Okay, 4 or 5 problems we have to study. So you read this particular problem. For a cascode MOS mirror utilizing devices with VT equal to 0.5 volt. VT is a a threshold voltage. Mu n COX. What is this? This is the transistor fabrication constant. That is your Kn dash. Va dash is the early voltage. It is Va dash, means early voltage per length. Okay, per unit length. That is 5 volt per micrometer. This is the aspect ratio W by L. I reference is being given. You have to find the minimum DC voltage required at the output and output resistance. Okay, so this is a problem in connection with the cascode MOS mirror. So you should be able to calculate two parameters here. One is the minimum required output DC voltage required at the output for a mirror circuit. So there will be always a minimum output required for the proper working of a mirror circuit, and also there should be an output resistance. So these two parameters you have to find out. So this is the minimum output voltage equation, which is nothing but thermal voltage, threshold voltage plus 2 times of overdrive voltage. You can note down this equation. So to find this VO minimum is a minimum DC output voltage required at the output terminals of a mirror circuit. Okay. So for this we have to find out the threshold voltage and VOV, overdrive voltage. To find overdrive voltage, you have to write the expression for I0, which is very much familiar for us from the first module. That is I0 is equal to half Kn dash W by L into VGS minus VT the whole square. Here I0 is 100, half Kn dash is 387, which is mu n into C naught x, into W by L is given 3.6 by 0.36 into VOV square. Solving this, you will get VOV. VT is already given, so just substitute here. So VT is 0.5 plus 2 times of VOV 0.227. You will get the answer of minimum output voltage. Now the equation for output resistance, you know. The output resistance of a cascode mirror is GM3 R03 into R02, which is same as that of the output of an amplifier. Okay, cascode amplifier. GM3 R03, what it is? GM3 R03 is the intrinsic gain of the transistor, third transistor Q3. R02 is the output resistance of second transistor. So multiplying the gain and the output resistance, you will get the overall R0. So to calculate R0, you have to find GM. You know the equation for GM is 2ID by VOV. ID is given, VOV just now we have calculated. So that is GM. Now we have to find R0. You know what is R0? R0 is VA by ID. VA is the early voltage. Early voltage can be find out only by multiplying the VA dash and length, because VA dash is the voltage per unit length. So when you have the voltage per unit length value, multiply with the overall length, so that you will get the total voltage VA. Okay, so that total voltage is VA dash into L divided by the current ID, so that will get you the value of R0. So once you get the value of GM into R0, you can just put in this equation, because R03, R02, everything is same. All the transistors is matched. So no need to find R03, R02 separately. So whatever is the R0, that is nothing but R03 and R02, no change. Okay. So all those you can substitute in capital R0. So the equation will be, instead of GM, put a 881.057 into R03 0.018 mega ohm. Again R02 is same thing only. So we'll get the output resistance like 285 kilo ohm. It is 0.285 mega ohm. Can convert into kilo ohm. So answer is 285 kilo ohm. Understood the concept? So here the question was to find the minimum required output voltage of a mirror circuit at the terminals, drain terminal. So you have an equation V0 which is equal to Vt plus 2 VOV. So first of all, you have to find VOV. VOV can be find out by using the typical output current equation. So once you find the value of VOV, substitute in the equation Vt plus 2 VOV, that will get you the value of output minimum voltage. Next thing is find the output resistance of the cascode mirror. You know that the cascode mirror is a perfect one which is having the same output resistance as that of the cascode amplifier. You know that cascode amplifier is having an output resistance of GM3 R03 into R02, which is same as that of the output resistance of a mirror circuit also. So write that equation, but there unknown is GM. So you have to find GM. GM is 2ID by VOV. So find GM, then find R0. R0 is VA by ID. VA is VA dash into L, because VA dash is the early voltage per unit length. So when you multiply VA dash with the overall length, you will get the total voltage divided by ID. That will get you the value of GM, sorry, R0. Okay. Now once you get R0 and GM, you can substitute over this equation and find capital R0. Now second problem. For beta equal to 100, so beta 100 means it is a bipolar mirror, not MOS mirror. It is a bipolar mirror because beta has been given. R0 100 kilo. Calculate the Wilson mirror and the symbol mirror contrast. So not calculate contrast means you have to differentiate these two by evaluating the current transfer ratio due to finite beta and output resistance. Okay. So we need to compare the Wilson's mirror and the symbol mirror. Symbol mirror means nothing but the BJT's first version. BJT's base current compensation. That is a symbol mirror. Wilson's mirror means Wilson's current mirror, bipolar version. Okay. So we have to compare these two for the given value of beta and R0. So first of all, we'll be comparing with respect to R0. You know that output resistance R0 is equal to beta into R0 by 2. This is for the Wilson's mirror. For Wilson's mirror, we have derived that output resistance is beta R0 by 2. For symbol mirror, you know that for symbol mirror always R0 equal to R0. There is no change. Okay. R0 is equal to R0. That is small letter R0. Small letter R0 is the output resistance of the transistor. Whereas in the Wilson's mirror, there is some enhancement in the output resistance which you can observe in this equation. So substitute the value of beta 100 into R0, it is given 100 by 2, 5 mega ohm. Whereas in the symbol mirror, you are having only the output resistance R0 which is equal to 100 kilo. So got the difference between these two. So Wilson's mirror is able to produce a better output resistance when compared to the symbol mirror. Again, while calculating the transfer ratio, in the Wilson mirror, the error is 2 by beta square. You know that I naught by I ref ratio, you remember that equation, no? I naught by I ref is equal to 1 divided by 1 plus 2 by beta square. Actually, the 2 by beta square is producing an error. If 2 by beta square can be neglected, it will be 1 is to 1. 2 by beta square will be always 0.000 like that. Okay, so that is the actual error which is incorporating in the Wilson mirror. We are expecting a current transfer ratio of 1 is to 1. Okay, so 1 is to 1 we get only if 2 by beta square is negligible. So that 2 by beta square is acting as an error for current transfer ratio. That is known as transfer ratio error. So as far as a Wilson mirror or bipolar Wilson's mirror is concerned, the error is 2 by beta square. That you can find out. Beta is given. So 2 by 100 the whole square. When you express in percentage, you have to multiply again with 100. So answer is 0.02 percentage. For a simple mirror, the error is 2 by beta. That is a difference. See, so the difference here is error is more in simple mirror. So you won't get 1:1 exact ratio for a simple mirror. So though you are expecting 1:1 ratio, but because of this high percentage of error in a simple mirror, you won't be get 1:1. While in a Wilson mirror, there is a chance to get 1:1 because the error is 2 by beta square. You know the 2 by beta square's value is quite close to 0.02 percentage means it can be negligibly very small. So the approximately you will get I naught as equal to IRF. So whatever be the IRF, that will be steered as I0. Negligibly the error is small, approximately 0.02 percentage. But when goes to simple mirror, there is 2 percentage. Means you will not get I0 same as that of IRF. There is going to be some mismatch between I naught and IRF. That is because of this 2 by beta value. The earlier it was 2 by beta square. That is appreciably okay. It is desirable. But this thing has got some problems. So that is a distinction between Wilson's mirror and the simple bipolar mirror. Simple bipolar mirror is having an error of 2 by beta. At the same time, Wilson's mirror is having a less error of 2 by beta square. Remember that beta is very large. So 2 by beta square is quite small when compared to 2 by beta. Now, last question. I think this question has been given as assignment, but this is very important question. Okay. Please note that problem number 3, the last problem of this particular module is very important. This is being given as assignment to you. But to do this problem, I should compare the performance of the common source and cascode amplifier, whatever we have studied in this module. Okay. So in this module, we have already discussed about the cascode amplifier. The cascode amplifier's intention was to increase the gain. Okay, so it is able to provide better gain of A0 times when compared to CS. So CS is providing a gain of GM into R0. At the same time, the cascode amplifier is offering better gain. Okay, it is offering better gain because it is having two stages. So CS stage and CG stage. So when you combine these two, it is able to produce a better overall gain A0 times when compared to the conventional common source stage. So this is the expression for the open circuit voltage gain. This is the expression for individual gain for CS and CG because you know the cascode you are having both CS and CG. In the second term, we'll compare the overall voltage gain. Overall voltage gain is AV. You know the equation difference between open and overall. Overall means we have to consider the load also. Here we are not considering RL. Okay. While writing the expression for open circuit voltage gain, we will not consider the load resistance, but while writing the equation for overall voltage gain, we will consider the equation for RL also. Okay, that RL term is to be included. So this is the equation for AV for CS, but when we go for a cascode amplifier, the equation for AV will be like this. That is AV equal to AV0 into RL divided by RL plus R out. AV0 means AV0. What is AV0? That is the product of two stages. You're having two stages CG and CS. So individual gains we have to multiply to get AV0. So that AV0 into RL divided by RL plus R out. You know what is R out? R out is output resistance of second stage. Second stage is common gate. That is R02 plus AV02 into R01. So this will be remembered only if you have thorough practice with the derivations of cascode amplifier. So sit and practice and then try to do this problem. So even if I explain this problem, you won't be able to get an idea, but that idea will be, you will get that idea provided if you have practiced everything. But just try to understand the concepts. Okay. So this is a comparison between the overall voltage gain. Now this is a comparison between the total time constants. So this is the equation for tau h for CS, but in cascode amplifier you are having tau h as given here. See, you are having three distinct terms here, that is tau h. So to find the tau h, you need RD1. So the equation for RD1 is given, and you need R out also. The equation for R out is given here. So all these we have derived in the small signal analysis of cascode amplifier. Okay. So try to practice and then analyze these results, and based upon these results, we are going to do this particular problem. So the problem's intention is to compare two different cases. One is with RSIC and second one is without RSIC. You know that in a cascode amplifier, there are chances when you connect RSIC. RSIC is a signal resistance at the input terminals, and there are circuits where you won't connect RSIC. Okay, so there is quite comparison between these two cases. Okay, if you are having RSIC means it will lead to some other cases. If there is no RSIC means there will be a relation like that bandwidth gain product will be always a constant. Okay, so gain bandwidth product of a cascode amplifier will always be a constant, but provided there is no RSIC. RSIC should be equal to 0. Okay, that is a condition. RSIC equal to 0 condition will only take you to this particular relation. What is the relation? Gain bandwidth product remains constant. That is, whatever the gain you had enhanced in the cascode amplifier, that much bandwidth you will be compensating. Suppose you have increased the gain 3 times, means you have to sacrifice the bandwidth to 1 by third, means your gain bandwidth has been product has been become a constant, but that condition is satisfied only if RSIG equal to 0. If RSIG is not equal to 0, this condition will not be satisfied. So that we are going to interpret in this particular problem. So try to read that problem. This is very important. Assume that all the MOSFETs have W by L ratio is same. Okay, so all the MOSFETs are having same aspect ratio. It is given ID is 100 microampere, GM is given, chi is 0.2, means you have to take the body effect into consideration. R0 is given, CGS, all the this thing, junction capacitances values has been given. CL is also given, 5 femtofarad. Compare the performances of the two amplifiers, that is cascode and common source. There are two amplifiers, you have to compare the performances for two different cases. One is with RSIC and second one is without RSIC. Okay. So you have to do these two cases with the given parameters. The given conditions or constraints are, first case, you will be using RL equal to R0, 20 kilo ohm for both amplifiers. So case A has to be done. What is case A? Case A means with the RC case. So with the RC case is to be done with load resistance RL equal to R0. But if you are not taking RSIC, then what you have to take is you have to take RL equal to R0 for CS amplifier. For CS amplifier, RL equal to R0. Okay, no change. But for a cascode amplifier, you have to take RL equal to R out. RL should be equal to capital R out. You know what is the difference between R0 and R out? R0 is the 20 kilo ohm which is given in the question, whereas R out is the overall output resistance of common gate. So that should be exactly matched for a cascode amplifier. So RL should be equal to R out for a cascode amplifier is to be done. Okay, so this is to be considered for case 2, case B. Which is case B? RSIG is negligibly small. Case A means RSIG is considered as 10 kilo ohm. Case B means RSIG is negligibly small. Okay, I repeat the question once more. So all the items have been given, all the parameters of the question has been given. So based upon the available parameters, we are going to compare the performance of the common source as well as the cascode amplifier. Okay, with respect to two different cases. Case A with RC given 10 kilo, case B without RC. RC is equal to 0. So these two conditions you have to perform. Okay, these two cases you have to perform and compare the common source and cascode amplifier. But certain constraints have been given. The constraints are for the load resistance. The load resistance value RL should be equal to R0, which is further equal to 20 kilo ohm for both the amplifiers. That is for both CS and cascode amplifier. But this case is applicable only for case A. That is, you have to take RL equal to R0 equal to 20 kilo ohm for both CS and cascode amplifier for case A. What is case A? Whenever you are taking RC equal to 10 kilo ohm. But when you are violating or neglecting RSIC, or if there is no RSIC in your circuit, then what you have to do is for CS amplifier you have to take RL equal to R0. Okay, but for cascode amplifier you have to take RL equal to R out. What is R out? R out is output resistance of CG, that is second stage. Understood? Now, first case, case A. Case A means RC equal to 10 kilo ohm. That is, you are taking the signal resistance. For that, you will be comparing the performance of common source and cascode. So first of all, we will be deriving the expressions for common source. So common source amplifier, first of all, we will be writing the equations for AV and then tau H. So find AV. All the parameters are given. This is the equation to find the voltage gain. This is the equation for finding tau h. Say all parameters are given. So once you find tau h, next thing will be finding FH by this equation 1 by 2 pi into tau h. See, your cutoff frequency is 155 megahertz and your gain is minus 12.5. So this was the two parameters that you have derived for common source. Understood? The gain is 12.5 and at the same time your cutoff frequency is 155 megahertz. Now this we will be comparing with the cascode amplifier for the same case. Same case means with RSIC. Okay. So with the RSIC, you are again going to calculate the equation for voltage gain AV. So this is the equation for AV. To find AV, when you observe this equation, you want to find AV0. To find AV, you have to find AV0. So to find AV0, you have to find A01 and AV02 because you know that in Cascode you are having two stages. So one is CS and one is CG. So individually you are going to find the gain of two transistors and then you are going to product these two. That is nothing but AV0. So first of all, you will find A01, then you will find AV02. So all the parameters are given. So once you study the equations by heart, just substitute the given parameters so that you find A01 and AV02 individually and then you multiply and see your gain has become 775. So now you got AV0. RL you know. RL you have to take, it is given in the question that you have to take RL as R0 which is given. Okay. Now the only left parameters are out. R out is the output resistance of common gate. This is the equation. So all the parameters have been given. Substitute, you will find R out. So everything you found out, then you will get AV. See, now your gain has become minus 23.5. Your gain has become minus 23.5 from the previous case. In the CS case, it was 12.5, I think, isn't it? So from 12.5 gain, now you have increased your gain to, see, this was a gain for the previous version CS, but when you are using Cascode Amplifier, your gain has been increased from 12.5 to 23.5. Now let us check what is the effect on cutoff frequency. Earlier your cutoff frequency was 155 megahertz. Now for the Cascode Amplifier, you are again finding the cutoff frequency. Your equations will be different. So write that equation, all the parameters you find out, substitute, you will get the value of FH as 244 megahertz, that is it has been increased. Means your gain has also increased, your cutoff frequency bandwidth has also increased. Means the gain bandwidth product constant, that theory is not applicable for this case. Understood? This case is RSIG is equal to 10 kilo ohm. We have taken RSIG, an appreciable value or definite value of RSIG you have taken. So when you take RSIG means your bandwidth has also increased, your gain has also increased. But see, you have no appreciable increase in gain. Only 12.5 has been increased to 23.5. Okay. But now I'll try to neglect RSIG and check what is the effect on our gain and bandwidth. That is case B. Understood? I hope you are getting the concept. Okay, so study the formula, study the derivation, study the formula and then do the problem. That is the only way how you can tackle this particular problem. It is quite important also. So case B, RSIG is neglected. You will calculate the common source gain. Again, it is 12.5, no change. Okay, because the gain of common source amplifier, it is independent of RSIG. But when you go for the cutoff frequency, it's again it is, see, when you go for the cutoff frequency, RSIG is equal to 0 means one term will go. So again your cutoff frequency has increased to 1.06 gigahertz. So this is the cutoff frequency of a common source amplifier when RSIG equal to 0. At the same time, when you go for the Cascode Amplifier, your gain has been increased to minus 388. See, very large drastic increase from 12.5 to minus 38, 388. So a very appreciable increase in gain you got in a Cascode Amplifier. So definitely you have been explored the advantage of Cascode Amplifier. So I repeat, the Cascode Amplifier will become beneficial only if you take convenient load value and convenient RSIG value. RSIG you should not use. Negligible RSIG you have to use. At the same time, you should be able to provide an appreciable load resistance also. You know that load resistance here is equal to R out. Because it is given in the question, you have to take RL equal to R out. Then only you will be able to get high gain. Okay. That is what is the intention of taking load resistance which is matched with the output resistance. Then only you will get a appreciable gain. So in this case, in the question it has been given that you have to take RL equal to R out. So when you take RL which is equal to R out, that is 640 kilo ohm. See, both are 640 kilo ohm, isn't it? Then you are getting a gain of minus 38, which is very much large. So a high drastic increase in gain has been achieved in the Cascode amplifier. At the same time, when you look the cutoff frequency, again you set RC equal to 0, write the main equation, and in that set RC equal to 0, derive the equation for tau h, all the parameters you derive and substitute and find the value of fh, you will get 31.2 megahertz. So the earlier cutoff frequency of common source was 1.06 gigahertz, isn't it? But now the cutoff frequency has been decreased from 1.06 gigahertz to 31.2 megahertz. So I will try to find how much decrease has occurred. Okay. Earlier the gain was 12.5. From 12.5 it has been increased to minus 388. So just you find the multiplication factor, 388 divided by 12.5. So that much gain has been increased. That is a multiplication factor actually, 388 divided by 12.5. The same factor is compensated for bandwidth. Okay, bandwidth, it is 1.06 gigahertz for common source. It is okay. But the thing is that when you're trying to optimize the gain of a cascode amplifier, you will have to sacrifice in bandwidth. See, this bandwidth 1.06 gigahertz, now it has depleted to how much? How much it is? Yeah, 31.2 megahertz. So once you divide that gigahertz, 1.06 gigahertz with 31.2 megahertz, again you will get a multiplication factor. That factor will be same as that of the factor where you have achieved your gain. Okay. So whatever, how much gain you have enhanced, the same factor you are going to compromise in the bandwidth. That is a speciality of a cascode amplifier, provided there is a condition, provided whenever you set RC equal to 0 and the load resistance RL should be same as that of the output resistance. R out is nothing but A naught into R0. R0 is the output resistance of CS stage. Okay, CS stage is having small letter R0, but the CG stage it is having A0 into R0. That is the actual R out. Okay, so that R out should be equal to RL, then only you will get this much gain, a very large increase in gain. But a very large increase in gain is going to affect your bandwidth. That is, bandwidth is coming down with the same factor, so that you can say that the gain bandwidth product remains constant. Understood the concept? Any doubts you can ask. So this problem is very important. If you have any doubts, means you can ask. Clear, no? Everybody clear? Shiva, clear, no?
Yes, sir.
Okay, so that is the end of this module. So this was pending only, so I just took this. Okay, then thank you all.
Thank you, sir.